This is the brief on mathematical symmetry and vanishing tensors. We're diving into a really fascinating area where extreme mathematical structure, specifically symmetry, can completely dictate the outcome for a physical quantity, which we call a tensor. And the challenge here is to show that a certain type of tensor has to just vanish, become zero, if it follows a very strict set of rules. First, let's talk about the mathematical constraints that force this to happen. The core finding is that these symmetry requirements are just so incredibly limiting, they leave no other option. If this tensor has to satisfy both of two specific properties at the same time, one related to swapping its parts and getting a negative, the other swapping and getting the same thing, it gets locked into being zero. Second, we've got a great way of visualizing what's going on with these tensor components. You can actually map all of this abstract math onto a 3D scatter plot. Just think of each point's position on a grid directly corresponding to a specific component based on its indices. It's a direct, visual, one-to-one mapping. And finally, this is how we link the theory to what we can observe. See, a non-zero tensor would look visually rich on that plot. You'd see points of all different colors representing all the different values. But the zero tensor, the one the math forces into existence, well, it's visually uniform. Every single point is the exact same color because every single component is zero. So those specific, strict constraints of symmetry guarantee that the quantity must be in a state of complete uniformity.